This is our lecture number 11, I believe. So in this lecture we're going to finish the topic of estimation, and in the previous lecture, number 10, we discussed estimation of the population average, mu, based on a sample, right? So we're getting n observations, the more the better, and from this sample we compute x bar, and then we also estimate the something called margin of error, and from x bar we go margin of error up or margin of error down, and that gives us a upper and lower confidence limits, and we're x% confident, whatever that might be, 90, 95, 99% confident, and between the lower and upper confidence limits we have captured successfully this holy grail, okay, population mean. Well, in this lecture number 11, we're going to take a look at the same exact problem, estimating the population parameter. But in this case, it's going to be about categorical data. So the previous problem that we looked at was FedEx workers package sorting productivity, right? And the data was numerical, so we recorded about each and every person how many packages per hour were they able to process. Okay, so in this part we're going to actually use a different example. Let's say there is an exit poll, right? So every time when there are elections, especially big elections such as presidential, all TV companies, they conduct their own exit poll. So what's an exit poll is just a bunch of people who are exiting the voting place, voting booth, right? They're being asked, can you tell us which candidate did you vote for? And they collect number of responses, and from that typically they estimate which candidate is more likely to win, right? So let's use exactly that one. So how is the results are the results of the elections are being judged? It's the majority vote, right? So let's say Virginia, 8.5 million people live here. Okay, well, not everybody is eligible to vote, right? Until a certain age you can't vote, but everybody who can vote in the state of Virginia are considered to be the population, right? And at the end of the day, every single vote is counted, and then we know at the end of the day, this is one rare situation actually when we do have an access to the population data at the end of the voting process, right? So let's say that there are, I don't know, 7 million people who are eligible for voting, right, in the state of Virginia. So not all of them will come to vote, of course, right? Some people will stay at home, but let's say, I don't know, 5 million voters will show up, right? That's everybody who voted. So then all the votes, all 5 million of them, everybody who showed up, are being counted. So this is one rare example when the population data has to be processed, right? But when elections keep going, right, when they're not done, so pi, this letter pi right here, is our holy grail, right? At the end of the day, when everything is counted, what would be the actual percentage of people who voted for one candidate? Let's say Republican, okay? Because obviously it should add up to 100, right? So if 53% voted for Republican, that means that 47% voted for a Democratic candidate, and vice versa, right? So if we know one of them, we know the other. So at the end of the day, this is what we want to determine. What is the actual true proportion of people who voted for a Republican, let's say, candidate, okay? But as the elections keep going, the result is not set, right? It's not set in stone, and we just simply don't know. Data is not collected yet. So therefore, what we're trying to do when we conduct exit polls is try to collect a sample, and then from the sample try to conclude which candidate will win, right? So essentially we're estimating this number, pi. Again, we're using Greek letter for the entire population. In case where our data is numerical, we used Greek letter mu. Now we're using Greek letter pi for the proportions. Okay, so let's say that we are picking a group of people, 700 or 1500 or 2000 people, and every one of them we're asking, Did you vote for Republican or for a Democrat? So, and after that, here's what happens, right? We are going to record randomly. I can't remember where I put that. Republican as one, somewhere on the slides, I'm sure. Yeah, this one right here. Okay, so what we do is we collect n observations, whatever n might be. Okay, that's a sample size, and our outcome is either one, which is, I believe, Republican, or number two, which is a Democrat, or it can be vice versa. I can't remember, quite frankly, what was used for to encode this this data. Okay, so let's say one is Republican and number two is Democrat. Okay, so we randomly pick one of them. So we call it success. For example, all people who voted for a Republican candidate, that's outcome number one. Let's call it success. Another one, if they voted for a Democratic candidate, let's again randomly, there is no judgment involved, call it a failure, right? And that's what we're going to record, one or two. Okay, so one again stands for Republican, and number two stands for a Democrat, or it might be actually opposite in the file. Can't remember right now. Okay, so and here is the challenge though. Okay, each time when we ask a group of people, so let's say that we are going to ask n people, same number of people, again and again and again. So we're going to get different samples of the same size. Truth is, the proportion will be always different, right? And that makes sense. Let's say, for example, we settled for 500 people, right? So we take first 500 voters, and out of them, let's say, for example, 270 voted for a Republican. Okay, and then so x is 270 divided by n. That gives you what, 54%. Fine. Then we take next 500 people who exit the vote place, right? And we ask them, each one and every one of them, did you vote for Republican or for a Democrat? And now, among these 500 people, the percentage, the count of voters for Republican is, let's say, 245. And therefore, the 245 divided by 500, that gives us 49%. And that will happen again and again if we keep collecting the samples. So just like with the population mean, we collect different samples, we calculate sample mean, each time sample mean is different. And same thing here, okay? We're going to collect sample of the size n, count how many people voted for Republican, divide one by another, we're always going to end up with a different proportion. That's the problem, okay? So therefore, problem is very similar to the one that we looked at with FedEx example. P hat is something that we compute from the sample. So it's a sample proportion, and we're trying to estimate the actual final proportion when all the votes are counted and when we know the population parameter pi, the actual proportion. Okay, so that brings up an interesting question. Okay, just like what we did with x bar, how different proportions are distributed. So let's take a look. And again, I found a nice illustration for you online. So let's take a look at this website. There you go. Alright, so proportion sampling distribution simulator. So we are going to play around with a few parameters here. Okay, sample size. Let's say sample size is each time when I'm getting a sample, I'm asking 100 people, okay? And true proportion is 0.5, right? And number of samples to draw, well, let's start with 100 and let's see what happens. So I draw, well, let's actually increase that. I'm going to get 1,000 samples. So applied to this specific example, right? People coming out of the voting booths, and I ask them, who did you vote for? Each time I ask 100 people, right? And I ask 1,000 groups of 100 people, right? But at the end of the day, the true proportion is going to be 0.5. I know that right off the bat. Okay, so I'm going to get 1,000 samples, each sample with 100, and this is how the proportions are distributed. Look at that. I have a peak around 0.5, right? Well, that's because my sample, my population, the true proportion of successes was 0.5. Let me move it a little bit. Okay, so how about I make it 0.4, for example, right? just to make things interesting. All right, 0.4. So let me draw it again. Different bunch of samples. So see what happens. The peak is peak of this is sampling distribution. First of all, okay, it's the distribution of all possible p hats. So I'm getting 1,000 samples. Each sample includes 100 people, right? And in the population, 40% of them will say yes, or Republican candidate, okay? So my proportions will be all over the place, right? You can see that in some samples of 100 people, I'm going to get proportion of those who voted for Republican below 0.26, right? Somewhere over here. On the other hand, sometimes, every once in a while, I'm going to have as high as 0.54, even higher than that, 0.56, right? Some samples, even though the true proportion in the entire population is 0.4, some samples randomly are going to be high, right? But the majority of them, you can see, are going to be concentrated right around where the population proportion is, right? 0.40, okay? And what can we say about the shape? Shape looks pretty darn normal. It's PDN, right? Okay, so let me change that. How about 0.6? I'm betting I'm gonna see the same picture. Okay, let's draw. Alright, well, that one looks normal-ish, right? It's a little bit skewed to the left. Let's draw another one. That's normal, more or less. That's normal. Another pretty normal, another pretty normal, right? So every time I draw 1,000 samples, look at that, peak stays roughly at 0.6, right? So whatever the true proportion of the population is, that's going to be my center of my sampling distribution. This is distribution of all possible sample proportions, p hats, right? They're all over the place. Again, you can see some of them are as low as 0.4, even though the true population percentage is 0.6. Some of them go as high as 0.7, right? 0.72. But they're all centered around 0.6, right? And the shape again is normal, right? Okay, so let's take a look at what happens if I increase my sample size. So instead of 100, I'm going to get 500 people each time when I ask a group, right? Okay, well, that's interesting. Alright, this is normal-ish. This is normal-ish. So you can see that my distributions, they look pretty normal, right? I mean, there is nothing unusual. These couple of spikes, it does not mean that this is a bimodal distribution. It's just basically random stuff, right? Okay. And you can see that it's still, the peak stays around 0.6 and distribution stays around, and the distribution shape is normal. But what I was going to actually demonstrate with that, my variability went down. Okay, so let me, to make it obvious, let's go back to 100. So here you can see that my distribution, my sampling distribution ranges from roughly 0.45 to roughly 0.73, right, approximately. As I increase my sample size to 500, okay, the peak is still at 0.6. Look at the spread. Okay, now it's roughly from 0.54 to 0.66, right? What if I increase again? 700. Let's do that. 700. Yeah, I can't see really these numbers. That's a mess. Okay, but my point being is, as you increase the sample size, the distribution becomes more narrow. Okay, and that is the case, by the way. I forgot to mention that in the previous lecture. It is the same exact thing that happens with confidence interval for the numerical data as well. The reason is very simple. You divide by the square root from n. As n goes up, square root from n goes up as well. And when you divide by a larger number, you get smaller number, right? So therefore, your margin of error decreases as you increase the sample size. Same exact thing happens here, okay, in case of the population proportion. But the point of the story is the sampling distribution for the proportions, or distribution of all possible sample proportions, is normal, or very much approximately normal, okay? And we're going to use that property right here, okay? And that's just basically another slide that illustrates that here my true proportion in the population was 0.3. You can see it right here, 0.3. And possible percentages, they range from 0.3, from 30%. This distribution is symmetrical, right? Roughly speaking, from about 15% to somewhere, kind of hard to tell what it is, right? 47% or something like this, right? So you will get all kinds of samples with all kinds of proportions, but they're all going to be looking normally distributed with the mean around whatever your true population proportion is, okay? And we're going to use that property. So since all p-hats, all possible population proportions are approximately normally distributed, okay, that's exactly what we're going to use. Now, the properties are like this, okay? So if pi is my true population proportion, then I'm going to assume that all p-hats are normally distributed around pi, whatever that is in my population, and here is my formula for the sigma, okay? I have to take pi times 1 minus pi divided by n and take the square root from that. So that's the estimate of the standard deviation for this normal distribution, okay? Now, the only problem is, of course, pi is something that I'm trying to estimate. I don't know it. Not at the moment, right? So what do I do? Well, just like what we did with confidence interval for the numerical data, we use the next best thing, right? What can we get? Sample is the only thing that we have, right? We don't know anything about population, right? We don't know the true proportion pi, but what we have is a sample, and in the sample we can calculate p hat, the proportion in the sample, which is different from what is going to be eventually in the entire population, but that's the only thing that we have. It's the next best thing. So instead of pi in all these formulas, we're going to use pi hat, okay? That's your proportion from the sample. Proportion from the sample. N is the sample size. And so the idea behind the confidence interval with categorical data is very simple. It's very similar, actually. If you look at the formula, it's very similar to the confidence interval for the numerical data. What is the center for the numerical data, of the confidence interval for the numerical data? X bar. Here we're using p hat, right? There is no x bar, there is no mean. The data is categorical, so we can't calculate the mean, but we calculate percentage, right, of category 1 and percentage of category 2. So the sample proportion is your center of the confidence interval. Then we have, because the data are normally distributed, instead of t distribution we're going to use z distribution, and again alpha is your significance level. So we have to say, okay, what confidence level do we want? Let's say we want 90%, okay? So 1 minus confidence level, 1 minus 90 is 0.1, that's your significance level, alpha. And then again you have to divide it by 2 because, well, you're splitting it between the right tail and the left tail. And that is my estimate of the standard deviation. P hat, what I can calculate from sample times 1 minus p hat divided by the sample size. So plus sign gives you upper limit, minus sign gives you lower limit. And that's all there is to it. So let's go ahead and give it a practical spin. So this is where the encoding is. I was looking in the wrong place. 1 stands for Democratic candidate and 2 stands for Republican candidate. So we conducted an exit poll and picked a number of people. How many people, sample size, we don't know yet. It's all in the file right now, right? Based on this sample, can the network conducting the exit poll conclude that the Republican candidate will win the elections? Okay, so winning means we have to compare that against 0.5, right? If it's above 0.5, so he collected more than half of the voters, that means that Republican candidate won the elections, right? Otherwise, he lost the elections, all right? And what significance level do we have to use? I forgot. We choose here a 90% confidence. Therefore, significance level of 10%. Okay, so let's go back to the formula right here. So what I'm going to calculate first is, of course, p hat, right? And just look at p hat. And after that, we're going to calculate upper and lower confidence limits for the 90% confidence interval. Alright, so I'm going to switch to the RStudio. So this is my second problem, therefore I'm going to put a bunch of pound signs here. Okay, so thing number one is read data from CSV file, right? Always the case. So exit poll, I'm going to call that exit underscore poll. Okay, and that would be read .csv drive C folder data votes. I believe the file is called votes. Again, you have to download the file first from Scholar and move it into your data folder if you're using Windows machine, right? I did that already, so that's why I'm not stopping for this step. Okay, so the data is in. So first things first, right? Well, actually, you know what? This time around, let's take a look at the structure. Structure of the file, exit poll. I'm betting it's going to be one column. Yeah, so data frame, exit poll is a data frame. Sample size is 765. That's how many people I asked. And there is one column, one variable, and variable is called votes. Right now, R believes that this is integer, and it's hard to blame R, right? Because it's just a bunch of 2's and 1's. But we know that 2's and 1's, they mean something, right? 1 is a Democrat, is that it? I can't remember, hold on. 1 is the, okay, right here. Yeah, Democratic candidate, and 2 is Republican. So the question is, true or false, the Republican is winning? Okay, well, let's see. So first things first, let's estimate. So calculate proportions, right? And proportions, if you remember, are a couple of ways how we did that, right? Thing number one, first we have to create a tabular summary. Okay, so votes summary. Okay, and that would be, can you please give me the count of how many people voted? 1 Democrat or 2 Republican, right? So I'm creating a tabular summary from the exit poll data. Exit poll, the column votes. All right, now let's take a look at that, right? Votes summary, just for the heck of it. 358 voted for Democrats and 407 voted for Republicans. So it looks like Republican has more votes, right? So it appears that they're winning, right, based on that. But let's see. Let's not jump to the conclusions just yet. Okay, so next thing is I'm going to calculate the proportions, right? So votes proportions. I'm going to call it proportions. Okay, and that would be prop table, and I have to feed the vote summary into the prop table, right? Votes summary, and there it is. So let's look at votes proportions. Okay, so number one, and I believe one stood for Democratic candidate. Out of these 765 people that are included in our sample, 46.8% of them voted for a Democratic candidate, and 53.2% of them voted for a Republican candidate. So, based on just this point estimate, this is a point estimate, right? An estimation of what the votes should look like at the end of the day when all results are in. Based on just that sample of 765 people, 53% voted for Republicans. Looks like Republican is winning. Okay, how confident am I? Remembering that there is a distribution, right? If I take next sample of 765 people, votes will be distributed differently in this sample. It could be that now next sample will show that Republican is actually losing, right? So I can't really trust the point estimate, the proportion from the sample. What I have here is a p-hat. This is a p-hat, right? It's a point estimate of what the Republican percentage will look like. Okay, so now I'm going to need to construct a 90% confidence interval, right? But for that, I'm going to need to use z distribution, right? So now let me do the same thing exact, right? Confidence that I'm using right now is 0.90, 90%, right? So therefore significance level is 1 minus confidence, right? And I'm going to run both lines, one and the other one, because remember, if you type it, it didn't happen yet. You need to run this line. Okay. Okay. So according to my formula, let me bring back the formula. First things first, I need to calculate. It's somewhere here. Let me find it. Yeah, right here. Okay. I need to calculate the this portion, right? And just like for the numerical case, when the data were numbers, that is the margin of error. So I already have p hat, right? For the Republican candidate, p hat was 53.2% or 0.532. N, I know it's 765, but I need to extract that info from the data set, right? So I'm going to use n row function. And the other thing that I need is z value. Z, reminder, is a standard normal distribution with the mean of 0 and the standard deviation of 1. And I need half of my significance level in the right tail and another half of the significance level in the left tail. So let's get cracking. Okay, so here I'm going to say calculate, again pound sign, comment, calculate z value that gives, well, in this case it's 1 minus confidence gives me 10% divided by 2, that's 5%, so 0.05 area in the right tail, correct? Right tail. Okay, so and I'm going to call it just like here I called it t value, and here I'm going to call it z value. Okay, z value is, all right, so what do I do? Obviously I need to use the function q, right? Because p norm gives me probability for the normal distribution, and the q norm gives me the value given the probability. So here I have probability. Area is 0.05 in the right tail. So I'm going to use q norm because z is the standard normal distribution, right? Q norm function. And what is the probability? Well, just like what I did here. Okay, I'm going to do exactly the same thing. So I'm going to say it's 1 minus confidence, which I already calculated. Actually, it's significance, right? So let's use that. Significance. All right, divided by 2, right? 10%, split in half, 5 and 5. Okay. Next one is, unlike t-distribution, remember t-distribution takes only one parameter. That's number of degrees of freedom, df. Standard distribution, or normal, standard normal, normal, any normal, takes two parameters, right? One of them is called mean. And the mean for the normal, standard normal, is what? Mean is 0, right? And SD, standard deviation, is, for the standard normal, it is 1. And I'm looking in the right tail, which means lower tail is false. Okay? Upper tail is true, but there is no such thing as upper tail, so lower tail is false. Okay, so I'm gonna run this line, and let's see what the z value did I get. Z underscore value. Okay, it's 1.644. So that's the z that I'm going to use. Well, oh, and one more thing, right? I need, if I remember correctly, from the formula for the margin of error, I got p hat, I got z value, now I need n, right? Well, I know n, but it's important that my program also knows what n is. So sample size, right? Add extra blank line here. Sample size n. Alright, so I have n equals n row, number of rows, in my data set, right? And the data set is called exit poll. That's it. Okay, and it should be, let me check out, it should be 765, right? Yep, 765 it is. Okay, so now I'm going to calculate margin of error. Okay, so ME, just like I called it before, is equal to z value, right? I'm just acting according to my formula here. It's the z-value times the square root from p hat 1 minus p hat divided by n. That actually brings up an interesting question. Let's see if I can... so my p hat, because I'm interested in knowing things about Republican candidate, right? Here's my p hat, 0.53202, right? I can type it, of course, in the formula, but let's see if I can actually, even before I calculate the margin of error, if I can extract that value from my variable votes proportions. Because when I calculated proportions, I recorded them inside my, what supposedly is a vector, right? So first component of that vector is 0.4679. Second component should be that number, right? So let's see, if I take the vector votes proportions and look at the second element, that's what I'm supposed to get, right? And indeed I do. So second element of the vector votes proportions gives me the p hat, the point estimate or sample proportion, however you want to call it, of all voters who will vote in favor of the Republican candidate. So I'm going to copy that value into the memory. So margin of error, back to business, right? Margin of error is my z-value times, if you don't remember the formula, you can always look back into the slides, right? Z-value times the square root from p hat 1 minus p hat divided by n. Okay. Need to bring back the RStudio. So z-value times sqrt square root from p hat is that value, right? Votes proportions second element. That's everybody who voted for Republican. Times 1 minus that element. And that divided by n, which I already computed right here. N is number of rows in my entire data set, right? So second element times 1 minus the second element, p hat times 1 minus p hat divided by n, square root from the whole thing, right? So you have to make sure that these brackets, they include the entire expression, right? P times 1 minus p divided by n. Okay, so let's run this line and let's see how much is the margin of error. Margin of error is 0.296, so roughly speaking 3% margin of error. And now I can calculate upper confidence limit and lower confidence limit, right? So for upper confidence limit, I have my p hat, which is this one, right? It's voters proportion second element. It's everybody who voted for Republican candidate plus the margin of error around this line. And the lower confidence limit is same exact thing, p hat. So since it's sitting in the memory, I copied that into the memory. All I have to do is just Control V, paste it, right? Minus margin of error. And I run this line. And let's see, upper confidence limit is 0.5617. And the lower confidence limit is 0.5023. Okay, so now let's kind of briefly discuss what does that mean. Does that mean that we have a confirmation that the Republican is likely going to win or not? Well, in the previous case, in the previous lecture, when we looked at FedEx example, right, we couldn't say much, right? And the reason was that my lower confidence limit was below my target for 50 packages, right? And my upper confidence limit was above my target for 50 packages. So confidence interval was partially below the target and partially above the target. So I said it's inconclusive, really. I can't claim that my productivity is higher than 450 packages because it's possible that it's also below. Both options are included within my confidence interval. Well, what about now? Now I can see that my upper confidence limit is above 0.5 and my lower confidence limit is also above 0.5. And remember, how do we interpret the confidence interval? This one is 90%, right? So I'm saying that I'm 90% confident that whatever the final count, or not count, but rather percentage of votes given for Republican candidate will turn out to be, based on this sample, I'm 90% confident it's going to be somewhere between 50.2 and 56.17, right? Both numbers are above 0.5. What does that mean? That means that I'm 90% confident based on this sample that Republican candidate in fact is going to win these elections. Okay? So in this case, my conclusion was same as the one that I got from looking at the point estimate, right? This one right here, 53%. Both upper and lower limits are above 0.5. Therefore, I'm 90% sure that the true population proportion is also going to above 0.5. And as a result, the Republican candidate will win. Okay? So that concludes our lecture, but I wanted to illustrate one more thing. Okay? Remember when we discussed how the confidence level affects how wide is the confidence interval, and I told you that if you increase the level of confidence, your confidence interval also gets wider. And it's really simple actually to understand, because you want to be more confident, you will include more possibilities, right? And you will increase the chance that your confidence interval will actually capture the true mean or proportion, whatever that is. Okay, so let's take a look. My guess is that if I go up from 90% confidence to 95%, my confidence interval will become wider, and wider means that upper confidence limit will go up, but the lower confidence limit will go down, right? Let's see. So I change 95%, 90 to 95%. I rerun this one single line. No, actually, I need to rerun also because it changes the significance, right? Instead of 10, now it's 5%. And I have to rerun this line as well because it changes the z-value. Okay, number of rows doesn't change, but margin of error does change. And now margin of error is, you can see it went up, right? Remember before that margin of error, where was that? It was right here somewhere. Margin of error was this one right here, was 2.96, almost 3%. Now my margin of error is 3.5%. So indeed, when I increase my confidence level, the width of the confidence interval, which is twice times the margin of error, right, it also increased. So now my margin of error is higher. Upper confidence limit should go up, lower confidence limit should go down, and let's see. So before that, my upper was 56.1, well, let's call it 0.2, and lower was 50.2. Now my upper is 56.7, it did increase, and lower is 49.7, right, 0.66, which I'm rounding to 49.7. So it did go down. Okay, so same data, right? Nothing changed. It's just I want now to be more sure that the Republican is going to win. 95% instead of 90. And what do I see? I see that my upper limit is still above, not a big surprise, still above the 0.5 cut-off value, right? But my lower confidence limit now is below 0.5, okay? And it doesn't matter that it's only a small, teeny tiny fraction of that is below 0.5. Because that's one of the answers that I'm getting sometimes from students when I ask them, can I conclude now that the Republican is going to win likely? And the answer is no, really, okay? I'm 95% sure that the percentage of people who vote for the Republican on these elections are going to be between 49.7 and 56.7, okay? So small fraction of my confidence interval is below 0.5. Therefore, there is a chance that the Republican will actually lose. And that sample, therefore, does not give me an assurance, does not give me a reasonable assurance at 95% level that the Republican is going to win. Again, the reason is part of my confidence interval is below 0.5. But students sometimes tell me, well, but it's small part, it's really teeny tiny. The majority of the confidence interval is still above 0.5. So he's still going to win. No, we can't say that, okay? My confidence interval includes both possibility of losing and winning, okay? Therefore, this sample at 95% confidence interval does not really give me a statistical evidence to claim that the Republican is going to win. Okay, so that's the only change that I wanted to discuss with you. All right, that concludes our lecture. So it was shorter than normal. On the other hand, the previous one was longer than normal. So next topic that we're going to discuss in the next lecture is going to be a different form of inferential statistics, and from that point on, that's what we're going to be doing pretty much the rest of the semester. It's called hypothesis testing.